So, this is the third part of the lesson on wave motion. In this lesson, we will continue our discussion on waves by talking about a very interesting phenomenon called resonance. Now, what is resonance? Every object has a natural frequency of its own. What does it mean? Now, I have three beakers here. Well, I hope you can see those three beakers. Now, each of these has a natural frequency. Listen to this. Now, three beakers are different in size. That means they have different natural frequency. Listen to that again. Each object has a natural frequency. A bell has a natural frequency. A tuning fork has a natural frequency. If I hit this tuning fork, it will vibrate with a natural frequency. Now, I cannot make it vibrate with any other frequency. Now, you see, that has a natural frequency. Every vibrating object has a natural frequency. Well, a bell, no matter how hard you hit it, it always has the same frequency. But you hit harder, the sound will be louder. Now, a louder sound does not mean that the frequency is bigger. Now, if a swing is given a periodic push, have you ever taken a child to a park? Put the child on a swing and give the child a push. When the swing comes back, you give it another push. Each time you need to move back. Why? The swing goes higher and higher. We say the amplitude of the oscillation increases. Now, here I have something like a swing. Now, if you set it into oscillation, now watch when this oscillates. When it comes back, I'm going to give it a push. Now, each time it comes back, I give it a push. What happens? It goes higher and higher and higher. The amplitude of the vibration increases. Now, you remember in the last class we talked about amplitude of vibration of particles. The loudness of a sound can be increased by increasing the amplitude. So, what does this mean? If you have a vibrating object, you can make it vibrate with larger amplitude by applying a periodic force on it. That's what I did to this object. Now, watch this one more time. This object or this oscillating object has a frequency. Now, what does that mean? It goes back and forth a fixed number of times a second. It has a frequency. And look at this. The frequency of the impulse force is the same as the frequency of the swing. If the swing vibrates 2 times a second, the external force acts on it 2 times a second. Now, what happens here is the natural frequency of the swing is equal to the frequency of the force I apply. All right, I'm going to say that one more time. The natural frequency of this vibrating object is equal to the frequency of the external force that I apply. Each time the particle comes back, I give it a force. Is that right? So the frequency of the force I apply and the frequency of the swing are the same. then we say that the swing resonates with the force that I apply. Alright, listen to this again. The swing is resonating with the force that I apply. So what is actually resonance? Now here I have the example of the swing. Each time the swing comes back, you apply force. The swing will go higher and higher. It means when the natural frequency of the swing equal to the frequency of the external applied force, the swing will resonate and its amplitude will keep on increasing. And this phenomenon is actually called resonance. Here the frequency of the external force is the same as the natural frequency of the swing, and the swing vibrates with larger and larger amplitude. So I'm going to now define resonance for you. How can we define resonance? If a vibrating object is subjected to a periodic force with a frequency equal to the natural frequency of the object, the amplitude of vibration of the object will keep on increasing. This phenomenon is called resonance. Now, have you ever heard of an opera singer shattering a glass? You see, this glass beaker has a natural frequency. If I can produce a frequency that is equal to the natural frequency of this, the frequency that I produced will force this object to vibrate with larger and larger amplitude until it shatters. When the opera singer sings, she actually produces a large number of frequencies. If one of those frequencies is equal to the natural frequency of this glass, this will vibrate with larger and larger amplitude until it will simply shatter. Now, when I lived in Africa, I have seen this, I have experienced this. When a truck blew its horn, the windscreen of a car shattered to 1,000,000 pieces. Now, this doesn't happen all the time. It happens only when the natural frequency of the windshield equal to the frequency of the truck horn. It so happened that the two frequencies were the same. Now, the windscreen of this car resonated with the frequency of the horn, and it vibrated with larger amplitude and it broke. Now, have you ever heard of a battery of soldiers marching on a bridge and the bridge collapsing? Now, how can that happen? The bridge has a natural frequency. You know that a bridge, most bridges are erected on rollers. A bridge can oscillate. You see, a bridge has a natural frequency. When a battery of soldiers march on it, like left, right, left, what they are doing is they are imposing a periodic force on the bridge. If the frequency of that periodic force equal to the natural frequency of the bridge will start oscillating with larger and larger amplitude. And by the time the soldiers are at the middle of the bridge will simply collapse. And so, these days, soldiers are not allowed to march in formation when they are on a bridge. They are dispersed. You see, all these things illustrate that resonance is a common phenomenon in nature. Resonance always happens. That is, whenever the natural frequency of a vibrating object equal to an external periodic force, the object will then resonate with that external periodic force, vibrating with increasing amplitude. And this is what we call resonance. Well, let's now talk about stationary sound waves that are produced as a result of resonance. Now, the natural frequency of a stretched string is its fundamental frequency. Now, have you seen what a stretched string is and how we can make it vibrate? Now, here I have a stretched string. Can you see it is stretched from this end to here? This is a stretched string, and this has a natural frequency. Well, if I can subject this string to an external frequency, I have a machine here that will apply an external force on this and see how the string is going to resonate. I want you to watch how the string is going to resonate. Actually, now the string is vibrating. I'm going to increase the frequency of the external force. Now, I want to see if you can actually see this. Now, well, I think you can now see the two ends. I have a machine here. I'm going to change the frequency so that it's now going to vibrate. Can you see this machine operating? Now, watch what happens as I increase the frequency. Now, the frequency is very close to. Now, watch this. This string is now vibrating with very large amplitude. Now, what is happening? The natural frequency of the string is exactly the same as the frequency of the imposed force. Now, this lip that is moving up and down is forcing the string to vibrate. Now we have resonance. So this string is resonating with the frequency here. Alright? Now, this is the picture of the same I have in here. This is the mechanical vibrator I'm using. This will move up and down, setting the string into vibration, and the resonance occurs when the natural frequency of the string equal to the frequency of the mechanical driver. Alright? Now, so when the frequency of the mechanical driver equal to the natural frequency of the string resonates. Now, what happens? How does actually this happen? As the wave advances to the right and gets reflected, the energy of reflection comes here, and then the second wave is created at that time. That is when the natural frequency of the string equal to the frequency of the external source. That means the two energies are reinforced. Well, by the time the reflected wave gets back, the second wave is ready to advance. So the wave that is reflected from this end, when it reaches here, the second wave is ready, and these two will reinforce, producing a bigger vibration. So the energy of the second wave gets reinforced with the energy of the reflected wave, and this will continue reinforcing each other, and that is what creates the resonance. Now, when this happens, the string is said to resonate with the frequency of the imposed force. So what you see here now is the resonance of the string with the frequency of the imposed force. Now, the lip moving up and down is the imposed frequency, and that frequency is equal to the natural frequency of the string. Well, now the maximum displacements of the string occur at the center. Have you seen? The string has a maximum displacement at the center. If you watch the reflection on the screen. The string has maximum displacement at the center and no displacements at the fixed end. If you noticed, the two fixed ends, there are no displacements at all. Maximum displacement occur at the center. Now that means I have now got a drawing of that here. Now the point of maximum displacement is called an antinode. So here where I'm pointing, where the string has maximum displacement, is called an antinode. There, this is an antinode, and the points where the string has no displacements are called nodal points. So this has got a nodal point here and a nodal point here. There are two nodes and one antinode. So when the string vibrates like this, we've got two nodes and an antinode. So tell me, what is an antinode? An antinode is the point where the string has maximum displacement, and a node are points where the string has no displacements. Alright, now when the string vibrates like this, this is called the fundamental mode of vibration. In actual fact, the natural frequency of the string is called its fundamental frequency. And I can tell you what this frequency is. This is now 8.8, about 9. In other words, the string is vibrating up and down 9 times a second. And that is the fundamental frequency of that string. Alright, so here you have an antinode where you have maximum displacement, node and a node. Now, can you tell me, do you remember, what is the definition of a wavelength? A wavelength is made up of a crest and a trough. Do you remember that? Now, if you look at this wave, this has just one crest. If a wavelength is made up of one crest and one trough, now a crest alone is half of a wavelength. Let me see if I can draw that for you. Now, if this is a crest and that is the trough, and that distance is, we call, one wavelength, then the length of one crest is simply half of a wavelength. So, a full wave contains a crest and a trough. Therefore, the length of a crest alone is half a wavelength. Now, when the string vibrates like this, it has just one crest. You see that? Just one crest. So, the length of the string, the full length of the string, now is half a wavelength. I want you to understand that. The whole length of the string is now half of a wavelength. So when the string vibrates like this, the length of the string contains half a wavelength. The frequency of the string vibrating in this mode is called the fundamental frequency of the string. Now tell me, what is the fundamental frequency of this string that you see vibrating? Its fundamental frequency is 9 Hertz. And we represent the fundamental frequency by F0. F0 is the notation we use for fundamental frequency. Now, if V is the wave velocity, I hope you remember the wave equation. What is the wave equation that we did in the last class? The wave equation is V equal to F lambda. So, the wave speed is wave frequency times wavelength. Now, can you tell me what is the wavelength of the wave you see on the string? What is the wavelength of this wave? We said that the whole length of the string is half of a wavelength. So if I measure the length of the string, I'm going to measure the length of the string. Actually, I've made it exactly 1 meter. The length of the string is exactly 1 meter. Tell me, what is the wavelength of this wave? 1 meter is half of a wavelength. Therefore, the wavelength of the wave on the string is 2 meters. I'm going to write that down for you. Look at the top of the screen. The length of, I'm going to write it to the right. Now, the length equal to, length of the string is 1 meter, and therefore wavelength equal to 2 times the length, therefore that is 2 meter. You see, if the length equal to half of a wavelength, then the wavelength will be 2 times the length. So we have the wavelength is 2 meter. The wavelength is 2 meter. And can you calculate the wave speed? The wave speed is frequency multiplied by wavelength. What is the frequency? I said the frequency is 9 Hertz. So I can come here and calculate V equal to F lambda, that is F is 9 Hertz multiplied by lambda is 2 meter. Therefore, the wave speed is 18 meter per second. So this wave is advancing along the string with a speed of 18 meter per second. That is what it means. So the wave speed V equal to F lambda. Now, let us solve this equation for F. Can you solve V equal to F lambda for F? Divide both sides by lambda. We get F equal to V over lambda. Alright. Now, in this case, if F equal to V over lambda, in the fundamental mode, when the string vibrates like this, we call it the fundamental mode. So, if you replace this lambda by lambda equal to 2L, is that right? If you replace that lambda by 2L, we will get an equation for the fundamental frequency. So the fundamental frequency of the vibration of this string is V equal to 2 over L. Alright. If the frequency of the vibrator is increased to twice the fundamental. Now, I'm going to increase the frequency of this 2 times the fundamental. Now the frequency is 9 Hertz. Now watch the vibrations when I increase the frequency to 18 Hertz. Well, you can see, you notice that the frequency now is 12 Hertz. Now, is there any resonance? Do you see any resonance now? I increased the frequency. The frequency is now 12 Hertz. Why isn't any resonance here? Because the frequency of the string is not equal to the frequency of the external force. But if I now make the external force 2 times the natural frequency of the string, resonance will again happen. Alright, watch this. I'm going to increase the frequency to 18 Hertz. Alright, it is now 18 Hertz. And watch that. The frequency of vibration now is 18 Hertz. And now the string vibrates in 2 segments. Alright? So, if the frequency of the vibrator is increased to twice the fundamental, the string will resonate with two antinodes. Here there is an antinode, another antinode here, and how many nodes are there? There is one node, another node, another node. So, this time the frequency of the external force is 2 times the fundamental. And can you tell me what is the wavelength of this wave? You see, a wavelength contains a full crest and a full trough. Watch this. A full crest and a full trough. So what you see now is a full wavelength. That is, the length of the string now contains 2 full wavelengths. You see, from here to here is half a wavelength, and this now is a full wavelength. So wavelength now equal to the length of the string. Well, I have a picture here, but since you can actually see the vibration of the string, the picture is not very important. There you got the antinode, antinode, the node, node, and the node. Now, can you write an equation for the frequency of this? The frequency of this is 2 times the fundamental. Now, this is called the second harmonic. I want you to take note of some of these terms I'm using. If the fundamental can be called the first harmonic, and then the second mode of vibration is called the second harmonic. So the string is now vibrating in its second harmonic. Now, can I make this to vibrate with 3 times the frequency? Tell me, if I make the external frequency equal to 3 times the fundamental, what is 3 times the fundamental? 9 times 3, 27. I'm going to increase the frequency and see what happens. Well, you notice now the frequency is 23, the resonance has disappeared. You see, resonance occurs only when the external force has a frequency equal to the fundamental, 2 times the fundamental, 3 times the fundamental, and so on. I'm going to make the frequency 3 times the fundamental and see what happens. The frequency now is 27. You see what happens. The string is now resonating in its third mode. And what will you call this frequency? This will be called the third harmonic. And here, how many antinodes are there? This is an antinode, this is an antinode, and this is an antinode. There's a node, a node, a node, and a node. So this is the third harmonic. Well, you want to see the higher harmonics? Let's see here. I'm going to increase the frequency further and watch. This is the third harmonic you see. I'm going to increase the frequency to 36. To 36. And what do you see here? Do you see anything? There you are. The string is now vibrating in its fourth mode. Now this is called the fourth harmonic. So a stretched string can vibrate in many modes. The fundamental mode of vibration, when the string vibrates just in one segment, is called its fundamental or the first harmonic. When the string vibrates in 2 segments, the frequency is twice the fundamental, the second harmonic. If it vibrates in 3 segments, the frequency is 3 times the fundamental or the third harmonic. Now I have a picture of each of those. Look at that, the fundamental. If the fundamental frequency is N1, the frequency of the second harmonic is 2 times the fundamental, 2F1. The frequency of the third harmonic is 3 times the fundamental. The frequency of the fourth harmonic is 4 times the fundamental, and so on. I can go on and make the string vibrate in many higher mode. We will soon do a lab on this by taking measurements. Alright, let's now move on. Let me keep that away. Alright, let's do a lab work now. Now, what does the lab involve? Now, first of all, let's talk about this. A wave has the following characteristics. What are the characteristics of a wave? A wave has a wavelength. And I told you a wavelength is made up of a full crest and a full trough. And in the case of the wave that you saw, the length of a wave contains 2 full loops. Is that right? Yes. So a wave has a wavelength. A wave has a frequency. Frequency is the number of vibrations per second, or the number of waves produced per second. And a wave has a wave speed. Now, in this lab, we are going to study the relationship between the wave speed, wave frequency, and the wavelength. A relation between wavelength, frequency, and wave speed. All right, you should now tell me, what is that relationship? The relation between wavelength, frequency, and wave speed. The wave equation. What is that equation? Well, the equation is V equal to F lambda. Now, what we are going to do is, we are going to generate waves on a string, just like the ones I showed you. I'm going to repeat that. We're going to generate those waves and measure the wavelength, and then measure the frequency, and use those two values to calculate the wave speed. So, what are the measurements we are going to take? We are going to measure the wavelength, and we are going to use the frequency that we can measure from the machine. I will measure it and give it to you. Alright? So, we will measure the frequency, we will measure the wavelength, and then calculate the wave speed. That's what we're going to do. And now you must stop the video and get the worksheet. Now, print out the worksheet and bring it over and do the work with me. What I'm going to do is, I'm going to help you fill the tables with the values of F and lambda, and then you will calculate the values of V and complete the worksheet and then email it to me. Alright? Okay, let me set it up now. Well, I have set up the apparatus so that you can read the frequency. Can you read this value? That's actually 1.2. This string is now vibrating with a frequency of 1.2 Hertz. Just one vibration a second. Can you see it happening? Yes. But is it resonating? No, there is no resonance, because the natural frequency is not equal to the imposed frequency. Alright, what I'm going to do is increase the frequency so that we see the string vibrating in one segment. Alright, we're going to get one segment. I'm going to increase the frequency and watch this. Okay. Well, what is my frequency? This time, my frequency is 11 Hertz. 11 Hertz. Okay, I'm sure you can read it. So, let's write down that frequency. The frequency is 11 Hertz. Okay. And let's measure the wavelength. What is the wavelength of this wave? This now has just one crest. So if I measure the length of the string, I'm measuring the length of the string, and it is exactly 1 meter. I hope you understand that. This is exactly 1 meter. Alright? So half the wavelength is 1 meter. What is therefore the wavelength? The wavelength will be 2 meters. Okay? The next one you need to write on your own. Alright? I got the frequency 11 Hertz. The wavelength is 2 meter. Therefore, what is the wave speed? I'm going to leave it for you to do on your own. V equal to frequency multiplied by the wavelength. And I want you to write it with proper units. What is the unit of speed? It's meter per second. Alright? So here, the wave speed will be 11 times 2. That will be 22 meter per second. I'm not writing it down. You got to write it on your own. Now, what is the next part? I change the frequency so that I see the string vibrating in a second harmonic. Alright? I'm going to increase the frequency. What do you think the frequency should be for the string to vibrate in a second harmonic? Well, I'm going to increase the frequency to 22 Hertz. Now, watch this. The frequency is 22 Hertz. And now, you have the second harmonic. And what is the frequency? The frequency is 22 Hertz. I'm going to write that down. The frequency is 22 Hertz. Alright, what is the wavelength now? Can anybody tell me what is the wavelength? Now the string has a full wave. The string now has one full wave, a crest and a trough. So all I need to do to obtain the wavelength is to measure the length of the string, which is 1 meter. So the wavelength now is 1 meter. So the wavelength is 1 meter. And now calculate the wave speed. Okay, next I'm going to go to the third harmonic. Now the third harmonic is when the string vibrates in how many loops? There will be 3 full loops. So I'm going to increase the frequency so that we have the third. Yeah, there we are. This is the third harmonic. The string is now vibrating in its third harmonic. You have a node, antinode, a node, antinode, a node, and so on. Now tell me, how do I measure the wavelength of this wave? Now remember, wavelength contains a full crest and a full trough. So this is a full wave. In other words, a full wave contains 2 full loops. So all I need to do is measure the length up to here. Let's do that. From here to here. I got that length as 70 centimeter. I must write it in meters. Now 70 centimeter is how many meter? Is 0.7. Alright, so the frequency is 33 Hertz and the wavelength is 0.7 meter, and I want you to calculate the wave speed. Calculate the wave speed. Now I'm going to increase the frequency so that the string vibrates in its fourth mode. Alright, let's increase the frequency to there we are. Now I I need to adjust this because it's been sort of falling off. Okay. Well, this is the fourth mode of vibration. There is some racket in here, but the frequency is now 40. All right. There was a metal strip that was vibrating. So the frequency is now 45.6 Hertz. 45.6 Hertz. That is the frequency now. And what is the wavelength? Remember, wavelength is a full crest and a full trough. So I measure from this node to this node. That will be a wavelength. You see, wavelengths can be measured as the distance between two alternate nodes. That would be a good definition of wavelength. The distance between two alternate nodes. That's a node, that's a node, that's a node. Just measure that distance. Now, I get that distance exactly 55 centimeter. 55 centimeter is how many meters? 0.55. So, this time the wavelength is 0.55 meter. So I have the frequency 45.6 Hertz. The wavelength is 0. Remember, that's not 6. 0.55 meter. Calculate the wave speed. Okay, let's now go and look at the next mode. That is the fifth harmonic. Increase the frequency until we get the fifth mode. Alright, look at this. I lost it. Alright. No, I didn't get the fifth mode. Where is the fifth mode? There we are. Give me a second, I will have to reset it. Alright, here I have the beautiful fifth mode of vibration. You have how many full loops? Well, I said I got a beautiful one and it sort of failed me. Is that right? Alright, try it again. Well, I need to hold on to this because it is tilting off. Well, this is the fifth mode of vibration. Now, what is the frequency? The frequency is 61.6 and measure the wavelength. What's the wavelength? The wavelength is the distance between two alternate nodes. I can actually measure from this node to here. You see, the distance between any two alternate nodes. Okay, let's do that. And I get that as 40 centimeter. Alright, 40 centimeter. I'm going to write that down. The frequency is 61.6 and the wavelength is 0.4 meter. Let me cut that out. It is 0.4. Okay, I need to reset it again. Now, let's do one more. Let's get the sixth mode of vibration, or the sixth harmonic. Look at this. 1, 2, 3, 4, 5, 6. Aren't there 6 loops in there? Don't they look beautiful? There you are. And now the frequency is 75. Now you write it down on your own. I'm not writing it down. The frequency is 75 and the wavelength is, you can measure the distance between any two alternate nodes, and I'm going to measure the distance between this node and this node. That will be a full wave. Alright, let me measure that. And that distance is 36 centimeter. I'm not writing, you need to write that on your own. Well, the frequency is 75 Hertz. The wavelength is 36 centimeter. You need to write it in meters and calculate the wave speed. Okay. So, we measured the frequency and wavelength of each of the harmonics, and I want you to complete this table. You see, the last values I did not write. I hope you have those values. And complete this table and email it to me. Alright? Okay, we now talk about resonance of air columns. What we have been seeing so far is resonance of stretched string. Now, in the same way, you can set a column of air into resonance. Now, I have a column of air in here, enclosed inside this tube. Is that right? There is a column of air, and it has a natural frequency. You see, if I can set that into vibration by using an external force, if I vibrate this tuning fork and keep it at its mouth, and if the frequency of the tuning fork equal to the natural frequency of the air column will vibrate, giving out a very loud sound. Now, let's try this. Is the air column giving out a loud sound? Well, I did not hear a loud sound. Well, obviously it means the natural frequency of the air column is not equal to the frequency of this tuning fork. So I'm going to try another tuning fork. Let's try a second one. Let's see if the frequency of this will resonate with the air column. Did you hear a loud sound? Well, I didn't hear. Let's try a third one. Let's try this frequency. This is 440 Hertz. What does a Hertz mean? 440 vibrations per second. Now, well, did you hear that loud sound? The frequency of this tuning fork now equal to the natural frequency of the column of air there, and you hear loud sound. There you are. The air column is resonating. All right. So a column of air can be made to resonate with an external frequency. A column of air enclosed in a tube has a natural frequency of vibration. This column of air can be made to resonate with the frequency of a periodic force using a tuning fork. This is what I just showed you. When I kept the tuning fork vibrating at the mouth, the air column inside resonated. Look at this. A node at the fixed end and an antinode at the mouth. Can you tell me, what is the wavelength of the wave inside the tube? Now remember, a wavelength contains a full crest and a full trough. Now, let me show that one more time. Now, a wavelength means it must be like this. In other words, there is a node, an antinode, a node, an antinode, and a node. So, you must understand that a wavelength is the distance between two alternate antinodes, or two alternate nodes, or two alternate antinodes. Now, if this is a full wavelength, the distance between a node and an antinode, this is a node, this is an antinode. What is that distance? The distance between a node and an antinode, this distance is a quarter of a wavelength. Is that right? Because a full wavelength is from a node to the, not to here, the alternate node. So it is the length of two full loops. Now you have only half of a loop in here, and therefore the wavelength, there is only a quarter of a wavelength inside the tube. And therefore the wavelength of the wave here is 4 times the length of the tube. You see, the wavelength is 4 times the length of the tube. Okay. Now, when resonance occurs, a loud sound can be heard because the amplitude of vibration is largest at this time. Now, the particles at the mouth of the tube has the maximum displacement, and particles at the fixed end will have no displacement. So you have an antinode at the mouth and a node at the fixed end. The open end is an antinode, the closed end is a node. Now the higher harmonics of the air column can also be made to resonate. You can actually get the higher harmonics, just like you had higher harmonics in the string. Now, in the mode of vibration shown in the diagram, how many wavelengths are contained in the length of the tube? We answered that question. How many wavelengths? The tube contains a quarter of a wavelength. And can you write an equation for the fundamental frequency using V for the speed of sound in air? Now this time, the speed of the wave is the speed of the wave in air. So if V is the speed of the sound wave in air, can you write a relation connecting V, the speed, the frequency of vibration, and the wavelength? Alright? If you want to do that, I will give you 2 extra credit points. Write down a relation between wavelength, frequency, and the wave speed. Well, on a second thought, I'm going to withdraw that offer of extra credits because I'm going to do that for you. Why? Because we want to use it for our next lab. We're going to do another lab. Okay, now I'm going to do that for you. What did we say the wavelength of this wave is? Inside the tube, you have 1/4 of a wave. That means the length of the tube contains a quarter of a wavelength. How can I write it? The length of the tube contains a quarter of a wavelength. What that means is the wavelength to lambda equal to 4 times the length. So the wavelength of this wave is 4 times the length of the tube. We are now going to use this to set up an experiment to measure the speed of sound in air. Alright? Let's get along and do that. A lab to measure the speed of sound in air. Well, this is the experimental setup we are going to use to measure the speed of sound in air. Now, this is a tube that is open at the top. You cannot see that top. It is too high for me to show you the top. The top is open and you can see the length of the air column. I can change the length of the air column by moving this reservoir of liquid. If I move it, now watch what happens. When I move it down, there you are. You can see the level of liquid is decreasing. Can you see the liquid level falling? There you are. I can decrease the level, means I can increase the length of the air column, or I can decrease it by moving this up or down. Alright, so I can move the positions of the reservoir, move it up or down, and I can change the positions. Now what I'm going to do is I'm going to use first a tuning fork of 523 Hertz. So let me see if I can pull down your table. A vibrating tuning fork is going to be held at the mouth. Here I have the diagram. The vibrating tuning fork is going to be held there, and change the length of the air column by letting this liquid flow until you hear a big sound. And when you hear the big sound, when water is drained out of the tube, when you hear a loud sound, that is when the resonance occurs. Now when resonance occurs, the frequency of the tuning fork equal to the frequency of the air column. At that time, measure the length L of the air column. Well, if you measure the length L of the air column, what is the wavelength equal to? Wavelength will be 4 times the length of the air column. So your wavelength lambda, I'm writing at the top here, your wavelength will be 4 times the length of the tube. That's what we're going to do. We are going to change the length of the air column until you hear a loud sound. When you hear the loud sound, we stop the flow of the fluid, measure the length of the air column, and calculate the wavelength, that is wavelength equal to 4L. And that's what we will be doing. We will repeat it for different tuning forks of different frequencies. Alright? Occurs, an antinode will be at the mouth, a node will be at, in other words, a node will be here and the antinode will be at the mouth that you cannot see. And the length of the tube, this is the length of the tube that we're going to measure. We will measure the length of the tube. Tell me, what is the relationship that we established between the length of the tube and the wavelength when resonance occurs? The wavelength of the wave will be 4 times the length of the tube. So, the length L is the distance between a node and the antinode, and is equal to a quarter of a wavelength lambda. So the length of the tube equal to a quarter of a wavelength, or the wavelength will be 4 times the length. Alright, what I would like you to do is, once you measure the length of the resonating air column, I will measure it and pass it on to you. Calculate the wavelength using this formula. Once you got the length of the air column, calculate the wavelength as lambda equal to 4L. And then, using the wavelength and the frequency. Now, how do you know the frequency? The frequency is the frequency of the tuning fork. Remember, when the air column resonates, with the frequency of the tuning fork, what I'm going to do is I will vibrate a tuning fork and keep it at the mouth of the air column. Now you will not be able to see it because it will be above, it will be out of the screen, but you can hear the sound. Alright? And when resonance occurs, we will measure that length. So the frequency is the frequency of the tuning fork, and the wavelength will be 4L. Therefore, wave speed will be 4 times the frequency times L. You will calculate the speed of sound. Isn't that a nice experiment? To calculate the speed of sound in air using that formula, V equal to frequency times 4L, or 4 times the frequency times the length. And we will do this for 5 different frequencies. After doing the first, repeat this for 4 more values. Calculate the speed of sound each time and find its average value. So we will do that 5 times, and I will only assist you taking the measurements. You need to do all the rest of the work and obtain the average value of the speed of sound in air, and complete the table and everything about the lab and email it to me. Alright? And that is a good lab. Alright, let's set it up and start the lab. The first tuning fork I'm going to use has a frequency of 523 Hertz. That's correct. 523 Hertz. I'm going to write it down for you. The frequency of the tuning fork I'm using is 523 Hertz. Now, what we need to now do is to measure the length of the air column which will resonate with this. So what will I do? I will vibrate the tuning fork and keep it at the mouth. Can you hear a resonant sound? Well, I don't hear it. Well, it is not quite resonant. So what I will do is I will move the reservoir down to increase the length, and okay, now I will move the reservoir down to increase the length, and then I will try again. Now you notice that the length of the water is falling now. Alright. I'm going to keep it there and try it again. Well, what I will do later on is to use an adjustable clip so that the level will continue to fall, and then I can take measurements very easily. Alright, let's now try. Well, the resonance is happening pretty big time, is that right? Listen to that one more time. Well, the air column is really resonating. And now the length of the air column is 16 centimeter. Alright, you need to write that in meters. Alright, you need to write that in meters. The length is 16 centimeter. How do I write that in meters? Well, that is 0.16 meter is the length of the air column. Now, if the length is 0.16 meter, what is the wavelength? Calculate the wavelength. Now, when I write on the screen, sometimes it becomes difficult to read. Now, listen to this again. This is 0.16. That is 16 centimeter. Okay, now we repeat this by using another tuning fork. The next tuning fork I'm going to use is 440 Hertz. Alright, did you hear me say 440 Hertz? Okay, I'm going to write down that for you. The frequency of the tuning fork is 440 Hertz. And let's try if there is resonance. Well, I don't hear any resonance at all. Alright. Well, it doesn't sound like. What I need to do is reduce the water level. Let's see if I bring down the level, if I will get a resonance. Well, let's try that again. Well, I'm getting a fairly good resonance there. You think that's good resonance? Well, that is good resonance. And the length of the air column, you see, I can read it from here. It is marked out here. It is 19 centimeter. 19 centimeter is 0.19 meter. It will be 0.19 meter is the length of the air column. Okay, let's now use the next tuning fork. I have the next tuning fork is 392 Hertz. 392. So the frequency is 392 Hertz. Well, let's see if this will resonate with this length of air column. Well, I don't hear a loud sound, so I'm going to decrease or increase the length of the air column, and let's see, it's going to work this time. Alright, let's see if I keep it there. Okay. Alright. Now I'm going to try it again and see if it'll work. Well, do we have resonance? It doesn't sound like it, isn't it? Well, let's try the length a little more. Lower and see that will make any difference. Well, any experiment you need patience. But it looks like the resonance has passed, so I probably need to go back. Is that right? Okay, let me go back and increase the length a little bit and see what happens. Well, that's too much. Well, let's see. Well, I don't hear a resonance, so let's see. Okay, let's bring it down. Okay, try it again. There you are. It's getting close to resonance. I think it is fairly good resonance now. Is that right? Well, let me try a bit more. A little more increase. And maybe that will help. A little more. And see if that will help. Well, that actually passed the resonance, so I'm going to put it up a bit more. You see, we are taking a long time to find this. The first three was fairly easy. We found it very easily. But this one is taking some time. But that's okay. Is that right? Okay. So, yes, that's quite right. And the length there is 21 centimeter. 21 centimeter is how many meter? Well, it is 0.21 meter. 0.21 meter. Alright, now let's repeat with a fourth one. And what is the frequency of this? Let me read it. 349. The frequency is 349. And I need to increase the length in here, so let me bring it down and see whether I will get. Alright, 349, and let's try over here and see, we'll get a resonance there. Okay, let's try this. Well, I think it is fairly close to resonance, is that right? But not quite, so let me try that a little more and see any difference is there. You got to, what's the difference? Is it getting any better or worse? So that we can decide then what to do. It looks like it has been getting worse, so I'm going to take it back a bit. Okay, let's see. Take it back a bit. Okay, let's keep it there and try this time and see if we can get a resonance there. Well, that sounds pretty good. Is that right? That is very good resonance. Let's try one more time. Yes, and the length of the air column is 25 centimeter. 25 centimeter is 0.25 meter, is 0.25 meter. Okay, last one more, and the frequency of this is 261 hertz. 261 hertz is the frequency, so that will be 261. And let's measure the wavelength. Well, let's try this length and see if we get. Well, you hear nothing there. Let's reduce or increase the length of the air column by moving this down and see if we get any resonance. Alright, where do we keep it? Okay, let's try here. I'm going to try there and see whether we will get any resonance. Alright, listen carefully. Well, it is better we are getting resonance there, is that right? Alright, I think we are very close to resonance, so maybe a little higher. I'm going to take it a little higher. and see if that makes any difference. All right. Well, that's good resonance. So let's listen to that one more time. Okay, the length of the air column now is 33 centimeter. 33 centimeter, that is 0.33 meter. Okay, we have now finished taking the readings, and the rest is for you to deal with. Now, what do you do with this? You got the frequency, you've got the length of the air column. Calculate the wavelength. The wavelength is 4 times the length of the air column. And once you have the wavelength values, calculate the speed of sound using V equal to 4 times the frequency times the length. In other words, once you have the wavelength, simply multiply that with the frequency. You don't need this formula now, do you? V equal to F lambda. So just correct that top table like this. V equal to F lambda. Now, we don't need that formula because we have calculated lambda. We know F. So calculate your wave speed as frequency multiplied by the wavelength, and that is what you will write here. And you will have 5 values, and take the average of the 5 values, and that will be your calculated value of the speed of sound in air. Alright? And that has been actually a good lab. Let's now talk about musical instruments. You see, what we have been talking about so far is resonance. Now, resonance is the phenomenon by which musical instruments are constructed. You see, you've got a flute. What is a flute? A flute is setting the air column inside a tube to resonate with the frequencies you generate with your lips. Now, an organ, the church organ, has got many tubes containing air. You know that there are church organs that has over 1,000 tubes, and each tube will produce one musical note. What is a musical note? You see, this sound that you heard earlier, resonance of a column of air there. Now, if that resonates, did you hear this column of air resonating? Of course you heard. Well, that is a musical note. There you are. That's a musical note. A musical note is a sound of a fixed frequency. And once you arrange musical notes in some order, we get what is called a musical scale. Now, if you are familiar with music, you know what a musical scale is. You see, do, re, mi, fa, sol, la, ti. Haven't you heard of that? Arranging notes in order. You see, when you make notes in order, you make music. All music is produced by the arrangement of musical notes. And composing a music is arranging the musical notes to produce harmony. Is that right? So musical instruments make use of this property. All musical instruments. Now, what are the various types of musical instruments? There are wind instruments. I will show you some examples of that as we go on. There are string instruments. Piano, guitar, the violin are all string instruments. Percussion instrument, the drum, examples of percussion instrument, all use resonant vibrations of air, string, or stretched membrane. Now I'm going to pluck a stretched string. See whether you can hear the musical note. Did you hear the musical note? Well, that is plucking a stretched string. In a stringed instrument, that is what is used. If you look into a piano, you will see string of various length. As the length of the vibrating string increases, the frequency of vibration will decrease. All right. Now the quality of the note produced by a given musical instrument is due to the particular combinations of the overtones. You see, these musical instruments not only produce their fundamentals, but along with the fundamentals, they can also produce the higher harmonics. You understand what harmonics are? Harmonics are multiples of the fundamental. So when you actually pluck a string of a guitar, the sound you hear is not only the sound of the fundamental, but a combination of the higher harmonics. It is the combination of the higher harmonics that gives a musical note from a particular instrument its unique quality. And it is that unique quality that lets you identify if that instrument is a guitar, a piano, an organ, or anything like that. They all may be producing the same fundamental frequency, but you can distinguish these instruments by the fact that the combinations of the higher harmonics are different. Now, for the same musical note, the combinations of the overtones are actually higher harmonics, are different for different instruments, giving rise to the unique quality of the musical note that each instrument produces. I'm sure most of you can place the sound that comes from a violin as opposed to the sound that comes from a guitar, isn't it? Yes. What is that quality that makes you distinguish between these two? It's the combination of the higher harmonics. Now, a church organ is a wind instrument using individual pipes for each musical note. You see, this tube that I just showed you as resonating and producing a musical note. Now, this will produce only one musical note. And in order to produce good music, you need thousands of combinations of musical notes. That means you need thousands of these tubes. So next time you go to a church where the church has an organ, look for the tubes. Where are these tubes? Tubes will be very often organized in a very prominent place where everybody can see it. It will go from very long tubes to very short ones. It is the short tubes that produce the very high frequency. The long tubes will produce the low frequency. And it is the combination of thousands of these frequencies that gives the unique quality. Now, look at a church organ. This is the picture of a church organ of St. Stephen's Cathedral in Passau, Germany. Now, this is the biggest church organ in the world. There is no other church organs bigger than this. And how many pipes is this using? It uses 1,774 open pipes. In other words, it is not using pipes that is closed at one end. It uses pipes that are open at both ends. That gives high quality sound. And if you look, you have all kinds of pipes arranged in there. How many of them? 1,774 of them. Now look at the beauty of these kind of things. All right, let me now see if I can show you and produce some sounds by some typical musical instruments. Well, here I have several stringed instruments that uses stretched string to produce musical notes. You have violin, viola, cello, bass. Now try and listen to some of these musical notes. Alright, I'm going to play some of this for you. Violin, listen, it'll be playing only for a couple of seconds, so listen to that carefully. Well, that is our violin. Very typical, I'm sure most of you can figure that out. And this is our viola. Listen to that. Sounds very different, is that right? How about a cello? Okay, let's listen to the last one, that's the bass. Alright, so we looked at some string instruments. Let's look at some wind instruments. And first, the flute. How does the flute sound? Alright, let's listen to the piccolo. How about the clarinet? And oboe. Saxophone. Bill Clinton used to play saxophone. Well, let's leave the wind instrument and see if we can find some brass instruments. You can see the French horn. How about the trumpet? And tuba. A weatherman in Fort Myers used to play this tuba. How about trombone? Alright, let's just look at some percussion. Well, cymbals. How does cymbals sound? There you are. Snare drum and timpani. And finally, let's listen to the bass drum. Apparently that is quiet. Well, that's a nice way to end this, is that right? Now, what does it tell you? It tells you that each musical instrument has a unique quality. You are able to distinguish between one musical note and the other produced by each of these instruments. The unique quality of each of these musical instruments is due to the fact that they all have different combinations of the higher harmonics. Now remember, music is beautiful, and people say if you are a music lover, you will live longer. So a good prescription for healthy, good life is to learn to appreciate music, and if possible, sing and produce music, all right? And be a part of, make your life musical. That will give you more happiness. All right, okay, let's go on and do our last concept for this lesson. That is Doppler effect. What is Doppler effect? Have you ever experienced a car? You see, in America, the people don't blow their horn. But I have lived in countries where people drive continuously with their horn blaring. Now, if a car comes blaring its horn towards you, now can you make out how it is going to sound? Now, it's going to become shriller as it comes closer. And as it goes away from you, it sort of sounds flat. Now, I'm trying to imitate that. Just don't laugh. All right? It sounds like this. As it comes towards you, the frequency seems to be increasing. As it goes away from you, the frequency seems to be decreasing. Now, this effect is called the Doppler effect. Doppler effect is about the apparent change in the frequency of a sound as the source of sound either moves towards the listener or moves away from the listener. Now here I have a source of sound, and look at the waves that are coming from there. These are the waves that come to your ear and you hear. Alright? So this time the source is stationary and the listener hears the actual frequency. Alright. What happens if this source is moving? Now here the source is moving. I want you to watch this carefully. As the source is moving to the right, the waves on the right gets very compressed because the source is moving in that direction, and the waves on the left get compressed. So what happens when you try to listen from here? It is these compressed waves that reach you. That means more waves will reach your ear than the actual number of waves. So you hear the frequency to be very high. Now, on the other hand, if you are here, if you are now here, that source is going away from you. Look, the number of waves reaching you now will be less. Is that right? So if the source is moving away from you, the number of waves reaching you will be less. And if the source is coming towards you, the number of waves coming towards you will be more. So as the source moves towards you, you hear the sound of a high frequency. As the source moves away from you, you hear the sound of a low frequency. Now let me see if I can produce an imitation of that over here. If you want to pay attention here, I'm going to set a stretched wire into vibration. Now, I don't think you heard what I wanted you to hear. Now try and listen to this carefully. You see, that is the sound as the source comes closer. And listen to this. The flat sound. As the source moves towards the listener, the frequency increases and the frequency decreases. Well, Doppler effect has got a lot of applications. Now, if a source of sound moves towards the listener, the waves get squeezed. That means more number of waves will reach you. The waves reaching the listener are now shorter. The wavelength is small. That means more waves will be passing you per second. You will hear a high frequency sound. As a result, the frequency of the sound heard by the listener will be greater than the actual frequency. The opposite effect occurs when the source of sound moves away. Now, the waves get stretched in between the source. So when the source moves away, the waves get stretched and only less number of waves will reach you. You hear a low frequency. And that is the effect of Doppler effect. Now, let's see if you can listen to some Doppler effect. Let me see if I can access that. If I cannot, we will stop the lesson here. Did you hear how the frequency changed? Well, that is a good illustration of Doppler effect. Well, we spent a lot of time on this one lesson on wave motion. And remember, I divided this into 3 parts for the lecture, but for the homework and assignment, it will be treated as a single lesson called lesson 3.1. But for the lecture, I have divided into 3.1a, 3.1b, 3.1c, and so on. And now the third unit now contains another lesson that is on light that we will do later on. Alright? I will see you for that lesson a little later.